Perfect. Actually, that question was a fantastic segue into my talk, because I talk about community standards a lot, and it's been a big deal in my area of research over the past few years. So I work in an area called research to operations. So I take, cool new science results and develop tools for space weather forecasters for them. And one kind of essential component of operational space weather forecasting is the prediction of solar flares. So these are sort of like the oldest type of forecasts really in space weather. They've been forecasting them for decades in operational centers. And there are so many flare forecasting methods out there right now that proper evaluation of these forecasts is just absolutely crucial for us, the scientists, the end users, the forecasters, to understand the strengths and weaknesses of our methods. So we're going to talk a little bit about what we've been doing in flare forecasting for evaluation. And just as a quick kind of intro, to just remind people what I'm talking about in terms of forecasting flares, I'm talking about these, eruption of radiation across the entire electromagnetic spectrum, and we measure them in terms of X-ray flux as measured by the GOES spacecraft. So we have these A, B, C, M, and X flares, and for space weather we care about the M's and the X's because they're the big ones that are going to give you the big radio blackouts and the big GPS disruptions. And then in terms of prediction, we look to the source of these eruptions, so these sunspot regions, these dark spots on the solar surface that are regions of really strong magnetic field and crucially complex magnetic field. And that's really what's giving us a starting point for our forecast. We characterize this property of magnetic complexity in order to predict when flares might arise even from active regions, because we know that big complex regions are more likely to flare. So you might measure your total area, your total magnetic flux, your helicity of the region, or you might classify these regions like you can see there, alpha, beta, gamma, delta, super simple, but we know that the alpha regions are less likely to flare than the delta regions, and operations like to keep things simple. And then you take that measure of complexity, however you've classified it, and convert it into our forecast. And so for solar flares, we forecast probabilistically. We calculate a percentage chance of a particular magnitude of flare occurring over a certain period of time, and that's very much defined by the operational center. But that percentage value and how to calculate that percentage value is where the interesting kind of mathematical modeling comes in. Really flare forecasting work in operations has been pretty simple over the decades. Early forecasting work really focused on stats. So statistical methods based on historical flaring rates. That's a classic example of a table there from a Poisson technique that's very popular, that uses average flare rates of different complexity classifications. And that's really been the standard. But over the years we've built up more and more data to kind of deal with for statistics. So in recent times you've seen people starting to dabble in machine learning, and all different kinds of machine learning methods have been attempted on magnetic active region properties for forecasting. Support vector machines, random forests, artificial neural networks. Kind of name a first generation machine learning method, it's probably been done. But the caveat here is that they haven't really got to operations yet. And it's really important to know that whatever method is used, there's still a human forecaster in the loop. And the human forecasters don't quite trust these automated methods. They'll use their expertise to modify the probability values that are coming from these automated techniques before issuing guidance to users. Why don't they trust them, you might ask? And that's because of some very recent community evaluation that we've done to these techniques. And it all sort of kicked off in our field when we had quite a change in how things were working in the flare forecasting community, because we saw a massive surge in the number of flare forecast methods available. So this plot is showing the number of operational forecasts that are available publicly online for flares since 1992, and you can just see that massive increase when Solar Dynamics Observatory, so the NASA spacecraft, launched. Basically, we had a bunch of really high resolution data from an instrument called HMI of magnetic observations. Everyone wanted to do some cool science with some pretty data sets, and that left us with a really, really flooded market. And it's great to have options, but this can be really difficult for forecasters to know, which technique to use. What should they base their forecasts on? Especially the probability values really do quite vary widely from method to method. They all agree when there's no sunspots or when there's lots of them with loads of activity, but that in between can have a really large spread of values. So it makes it really difficult for forecasters to know which one is right, which one has the most skill without a proper evaluation of all these methods in a consistent way. And traditionally, we've been pretty not that great, I guess. I'll say we haven't been that great with evaluation. This is something that was very much done by, a lone scientist or a group of scientists writing a publication on their own research paper. People would generally just kind of copy whatever metrics they saw other people use in terms of evaluation, throw some numbers in the paper, done, kind of move on to the next thing. But with the different studies, there's different time periods that people were using with different numbers of flares. It was just really impossible to compare the skill of a newly published forecast to what was out there already. And in terms of what metrics, what I would call categorical metrics were being used, I know Mike sort of mentioned this already. So you convert this probability into a yes/no forecast using a threshold, and then you have this lovely contingency table to allow you to calculate lots of different skill scores. And I think that what was happening was that people were kind of picking their favorite metric and posting them in publications and using these categorical metrics. Our weather forecasting colleagues were pointing out to us, we were losing so much information because we predict probabilistically, but we were evaluating categorically. And that came from this ideal of a yes/no forecast or the holy grail of an all clear forecast. And that's something that, the science just isn't there yet to do, but we were sort of evaluating like it was. So chatting within the community, basically all the operational forecasting centers and some science centers who publish forecasts online got together in a series of community workshops over a number of years to define some new standards for our community, to create for the first time some proper operational forecasting comparisons. And it was quite the task, and it took us quite a while of lots of going back and forth, deciding what things to use. But we got there, and the first thing we had to decide was what metrics to use. And it was very much pushed forward by the operational community to start looking at probabilistic evaluation tools. So, some examples on your screen, you've seen the rock plot already. So, your hit rates versus your false alarm rates, and you want that curve to be in the top left of your diagram if it's skillful. And these are conditioned on the observations, so you'll often see a companion to them that are conditioned on the forecast, which are called reliability diagrams on the bottom there. And this time you've got your observed frequency of your events versus your forecast probability, and you want those to be equal. So your skill line is the diagonal. And they're really useful, I guess, visual tools. They're something they're used in weather forecasting a lot. And since space weather forecasts tend to be weather forecasters, they really get a good tangible link into what these sorts of skills mean. It doesn't limit you from, of course, calculating other metrics. It's just kind of an example here. And for the community, the key was us kind of publishing as much data as we could so other people could calculate whatever metrics they wanted to afterwards. And so after defining some metrics for our particular study, we had to define a data set, so a time period that everybody had forecasts for that had enough flares to make it useful, and also a benchmark. And this was a really complex discussion that I don't have time to go into details for, but if you're interested, I can maybe mention it later. Just trying to choose a standardized benchmark that everybody moving forward could then compare their forecast to, and we ended up with a rolling climatology for that. And that is the results of our hard work. So, after defining all these standards for our community, and we have about 18, I think, operational forecasts from all around the world that we compared in a series of papers as a kind of first step to show this to the rest of the world. So you're seeing for the first time standardized benchmarks, consistent data sets of metrics, allowing a really good comparison. I don't expect you to take all these plots in. I know there's loads of them there, but maybe note that in the rock plots, none of the curves are really in the top left. So they're not perfect. And in the reliability diagrams, none of those points are really perfectly along the diagonal. A lot of them are over forecasting. And really what we found is overall there's no one amazing method. None of them really outperformed all the others. I think a lot of people were expecting machine learning ones to do really well, and they actually didn't do much better than the Poisson statistics. The human forecasters generally tend to be the better ones, but none were actually substantially better than climatology. And it really kind of, I guess, gave us a sense of where we were with the science. It was a really, really interesting exercise and made us kind of step back and think about our science and how were we going to improve the models in the future. And there's been some really interesting progress in that, using sort of deep learning with images, moving away from the standard magnetic properties that we already are kind of using for decades now, that have produced some really, really good results. But I think it's going to be a while before any of that stuff is in any way near, operational. So it kind of begged the question to us what we can do in the meantime to help the forecasters, because now they have the results, they know they have a bunch of sort of mediocre models and they still don't really know which one to use as a starting point for their guidance. And so one method that we thought would be super, super useful for them, which surprisingly hasn't been used in flare forecasting before, is something called ensemble modeling. And taking from our weather forecasting colleagues, again, as per usual, this has been around for decades for them. It's even something that the public understand. This is a classic example of a hurricane forecast here in Florida. And so all the different colored lines are different hurricane models giving you, an idea of where the hurricane path might go. So it's a multi-model ensemble. And it's already been really successfully used in space weather forecasting already. A classic example on the right there is for arrival time prediction of coronal mass ejections. So this is kind of what's called a perturbed ensemble. So you have one model, but you vary the initial input parameters slightly with different model runs to give you this spread of arrival times. And that gives error bars for the forecasters, which is just an absolutely invaluable thing. And it's something, error uncertainty is something we're absolutely terrible with in flare forecasting. You'll never see a percent plus or minus a percent. And we definitely need to be, better at that. But baby steps, we'd never bothered running ensembles before. So that was the first thing to do. And we utilized that flooded market that I was talking about of all these different flare forecasts to create a multi-model ensemble for flares to see how they got on. And the results were really, really encouraging. And it's just amazing how something so simple can be really, really successful. So again, I'm just showing rock and reliability, just an easy kind of visual thing for talks. And what you're seeing here in the dark blue is an automated Poisson technique. So that was just the best automated technique in this particular data set. And the black line is actually a human forecaster. So they usually tend to outperform the automated method. And the purple is just a simple ensemble. Just take an ensemble average, literally just take an average of all the different probability forecasts. And you can see it ends up rivaling the human forecaster for this data set. So it pulls in the reliability diagram, and you can see the automated one is kind of going horizontal, which means it's tending towards climatology. So it pulls it out of that into the nice gray zone of skill. And it does really, really well. Super simple, but super effective, and a really great tool for the forecasters to have just a simple input to their guidance. And you can see a final thing I'll note there is this turquoise line. And that was something that actually ended up beating the forecasters for this data set. It's called a weighted ensemble. So you can create simple linear combinations with a weighting scheme and choose a metric for that weighting scheme. So what that means is that, it's a super, super flexible thing for forecasting. You can design an ensemble that's based on end user needs. You might want to mitigate misses. You might want to mitigate false alarms. Choose the metric that suits the user best. You might end up with lots of different ensembles depending on the user. So it's super, super flexible technique. And, it really kind of hones the point, which is very kind of similar to what Mike was saying, is I think the more metrics, the better, for sure, in anything that you do. I'm constantly discovering new metrics. The stone curve is fascinating, for example. I'm going to look that up later. Definitely the key is for sure to choose the metric that suits your type of data or model the best, but use as many as are useful to you. Don't just limit probabilistic evaluation to the rock reliability. This is from some colleagues in Heidelberg that look at precipitation forecasts and weather, and they have shown Murphy diagrams are really useful to add to rock current and reliability diagrams. So I'm constantly learning new metrics that are super useful. And the key for us in the community, I don't know what the planetary community is like, but we would just publish as much data as possible so that everyone can go ahead and calculate any metrics they want from our data sets. So that's it for me. Really just wanted to sort of highlight the point that I found that community kind of standardization has been just absolutely invaluable for us to kind of move forward our science in the fair forecasting community, and picking the right metrics and kind of getting out of that tradition of just, you know, copying a random number from one paper to another was really, really important, and understanding what the metrics do and finding the right ones for us were really important, and just having the conversations with the right people and having these workshops to push it forward was really important. They're just some useful resources that I find super helpful, some code bases if you want to run this kind of stuff. And this weather verification working group is like the Bible of metrics. It's an online web page that tells you everything about skill scores you'd ever want to know. So I'll leave it there for time for discussion, so I'm sure I'm running over.